Okay, so right now, as you can see, we start the session. So today's class, right, is going to be about order theory. So order theory, as you can see, is math basically that we use in micro, and you don't cover in the math for economics class. So it's a very simple reminder, almost like a dictionary kind of class. So my main objective here is for you to be able to be a little bit more acquainted with this idea of order theory. So again, so order theory is essential to understand decision theory. In particular, we model preferences using orders. We also then use utility functions, but the most general way to deal with these preferences is by using order theory. So let me put also my iPad, so I'm ready here. Okay, so what is a binary relation? Okay, let me know if you need this to be bigger, but we start with any choice set. So a choice set is basically a mathematical representation of a set of alternatives where the consumer is going to pick from. So examples of choice sets. So one example of choice set can be the set of all cars that you can buy in London, Ontario, right? Maybe you can make it more specific, all used cars. Maybe you can make it all even more specific, all used cars that are Honda, right? That's a choice set, right? And so we're going to start from this X, which is essentially, the grand choice set. So this is the universe of alternatives from where I'm going to pick from. And then I'm going to define a mathematical object, which is a binary relation R. And this is just a subset of the pair. So this is the product space of X times X. So what does it mean? It means that I basically have an order pair. So parentheses X comma Y, and the order matters. And this describes something. And in particular, we call this mathematically a relation. So an item X and then an item Y in that order, right? They are in a relation R. And typically in econ and sometimes in math, we describe these relations by this notation. So we say X is in relation R with Y, okay? Now, I want you to understand this is always a source of confusion. So I want you to understand that a relation, right, is an ordered pair, right? So it's this X comma Y. Now, the moment we write it like this, it's just a symbol for the fact that this X comma Y is an element of R. Remember what is R? R is X product X, right? So how do you build a relation? In particular, right? Let's go, for instance, to the example of the real line, okay? So let's say your choice set is the real line, okay? So this is where you're gonna pick from. You can imagine this is, for instance, the amount of depth you can go in, or how much, maybe you want to go short or long on something, so negative, positive, right? That's basically your choice set, is a real line, okay? Now, once you have that, I'm gonna define one possible relation. And this relation says item A in the real line is in relation with B, even only if A is greater than or equal than B. Okay? Now, so what I want you to understand is basically this. What is really happening is that A and B, is an ordered pair, right? And this belongs to R. Okay? So in particular, an example of this would be 1 and 2, right? They belong to this, which is equivalently written, right, as basically, sorry, this should be the other way. Okay. So, this is a concept that is so natural for you, the ordering on the reals, that you just, think of this as a symbol, right? So A is greater than or equal than B. Okay, nothing fancy there. You understand the object. What I'm telling you, right, is that mathematically this object means that it's an ordered pair, right? That means something. Okay. Now I can imagine other orders in the real line. Okay, so it's not the only order possible. Okay, so for instance, I can also define an alternate order. So I'm going to define an order okay. This order here, remember, is a subset of x times x, and it's going to be such that A is in this relation with B, if and only if 1A, 1B, B is not 0. Okay? This is another relation. Okay? This relation is defined like this. I did it because I wanted, right? It's another example. There is some form, you know, of, there is always a definition. Okay? Now, example 2, a more complex one. So say, so this would be an alternate order on the reals, on the reals. Okay. Now, so you don't believe there is only one ranking, basically, right? So basically, a relation just encodes some link between two alternatives, right? And basically, the modeler chooses what that relation is. The punchline here is that in the real line, the common one you use is the greater than equal, right? But that doesn't mean it's the only relation possible, right? There can be basically any relation there, okay? At this stage, the relation doesn't have any property, it's just this ordered pairs. So it can be anything. Another example is now say the choice set is R2, the Euclidean space, so a plane, okay? You have a plane now, and an element of this plane is, for instance, a vector, 1, 2. I'm going to define something that we're going to use for a lot of examples on problem sets called the lexicographic ordering, okay? What is the lexicographic ordering? Basically says A is better than B. What is A and B here? Both are vectors. Do you understand? So now A is a vector, B is a vector of size 2. A is in relation with B whenever, look at the notation. The first entry of the vector A, A1, is strictly greater than the first entry of vector 2, okay? And basically, if that's not the case, right? So basically, if that condition fails, then you enter an alternate condition, right? Which basically says, if A is equal to B1, then you have to actually compare the second entry, right? So A2 greater than or equal than B2, okay? So this is called lexicographic because there is some sort of priorities in the entries of the vector. So vector entry 1 is more important than entry 2, okay? Yeah, so, you know, lexicographic orders appear everywhere. So, you know, have you heard or read about the Maslow's necessity pyramid, something like that, right? That's an example of lexicographic preference. So you have some needs, food, shelter, right? And then you have other layers that are less important. So if you, for instance, you're offered a basket of things that include an element of each, basically each floor of the Maslow pyramid, you will use here lexicographic preference, right? First deciding which one is more important in terms of which one has priority, right? So any basket that at least has some food is better than other baskets that gives you a lot of culture, right? But doesn't have any food. That's kind of the idea, right? So that's the lexicographic order. And it's just one order. Now, one important thing that I want you to notice is this. So again, you can show some properties here. So in particular, we can do some training for a property I'm going to introduce later, and we use a lot in this class, which is called the completeness property. So a relation, as I said, encodes any kind of relation, so it's completely free now. So the only way it's useful for modeling is when we add properties to the relation. So one famous property to this relation is what is called completeness. Okay, we're going to go to completeness a little bit later formally, but right now informally, completeness means that any two items, A and B, are in relation to each other, right? So there might be relations where there is some pairs, A and B, that cannot be compared, okay? So they are incomparable, okay? Okay, so then a relation is complete when everything is comparable, okay? In particular, right, let's think about the lexicographic preference and show that it's complete. And then, you know, the next example is going to be an example that is not complete, so you understand this concept. So assume A is not in relation R with B, R being the lexicographic order. So we want to show that if that's the case, B is in relation with A. So that's a type of proof technique that is called by contradiction, right? So, sorry, again. So I want to show directly. So forget about the contradiction part. That's for the next part. This was a wrong statement. I want to show that these preferences are complete. So I'm going to just restate the completeness definition as a logical statement. So being complete means that if A is not in relation R with B, then it has to be that B is in relation R with A. That's completeness, right? These A and B are generic items in the choice set. So this statement is fully general. This is showing that A and B are in relation with each other, right? That's the only thing I'm saying. So let's start a proof. So if you have the first part of the statement, if not A or B, this means that either the second vector has higher of the main characteristic or the entry one than the first vector. So that means that V1 is greater strictly than A1, or A1 is equal to B1, right? And in that case, you know, B2 is greater than A2, because we know by the definition of lexicographic preference that if the two first entries are the same, in order for this not happening, right, it has to be that V2 is greater than equal than A2, just by definition. But if you go to the definition of the lexicographic preference, this is exactly the definition of B is in relation with A, because we're saying exactly this, right? Just relabeling, right? So we're saying now that B, the first entry is either above the first entry of A, or they have to be that the first entry is the same, but now the second entry of B is greater than equal than the second entry of A. So what this is saying is just a simple proof that lexicographic preferences are complete. So lexicographic preferences are able to rank every vector. Now, in order for you to understand this a little bit more, let's see another order. And this is the order of the vectors, right? The one you learn in linear algebra. So again, we have the plane R2, and you have two items, A and B, and we're gonna call them in a relation R. A is in relation with B, whenever A of the entry I is greater than equal than the corresponding entry in B for all entries, okay? For both entries 1 and 2. Now, I'm gonna give you just a counterexample that this order is not complete. So first of all, you understand the order? This is the simple order where you say this vector here is greater than equal than this other vector here. If entry by entry, right, they are greater than equal. Do you understand? This is the canonical vector order. Yet another type of relation, right? You can have some preferences. Remember, when I say preference, I don't say rational preference, right? At this stage, we have just some description of what people prefer, right? So imagine I have two goods here, right? I have food and I have, you know, books. and I have 1 unit of food, 2 units of books, right? In this order, I am asking you to compare the basket 1, 2 versus the basket 2, 1. According to the canonical order vector, which one is better? Is there any natural way to rank them here? Not really, right? Because my definition says that I can only rank them if entry by entry, one is greater than or equal than the other. Do you agree? So here, because it's not clear, right, which one is bigger, I cannot rank them, right? So basically notice that this example, basically 1, 2 is not in relation with 2, 1, nor 2, 1 is in relation with 1, 2, okay? So now you have 2 orders on the planes. One is the lexicographic order. The second one is the canonical vector order. The lexicographic order is complete. The other is not complete. Now, one source of confusion is that through the class, right, we have 2 kinds of objects, right? So we have preferences and relations. Relations is the mathematical name of this object, right? So it's just these order pairs. We use them to model preferences. Preferences can be rational or not, okay? Only relations that are complete and another property is called transitive are going to be called rational, right? If any of these properties fail, you are not rational, okay? For instance, if I have a preference model that basically is defined as the canonical order vector on the orders on the plane, then this will not be rational, right? Because it will fail completeness, okay? So the nice thing about econ modeling is that we're gonna equate this complex concept of rationality to 2 restrictions on preference relations, completeness and transitivity. We understood now what is completeness, right? Being able to rank any 2 alternatives. We're missing transitivity, okay? So we're gonna get there in a bit. Look at this. So I am still working with a canonical order on the vectors in the plane. I'm gonna show that they are transitive. So my next statement is gonna be a definition of transitivity. Take any 2 vectors, take any 3 vectors, in fact, sorry, there's a typo here. X, Y, and Z, they live in the plane, their vectors R2. And if I observe that X is in relation with Y is in relation with Z in this canonical order sense, we want to show that the first item X is in relation with Z. That's transitivity. So we're gonna use it a lot in this class. Transitivity, as I told you yesterday in the motivation of the class, is basically a property that lists, rankings, right? Order lists have, right? So if you are going through a list of alternatives, right? You will have this property. So if you have an item that is in the first position, right? And this is above a second item that is lower in the list. And then you have this second object in the list above a third object in the list. Then it's obvious that the first object will be above the third object, right? Because they are in a list, right? Basically, that's the natural property of a list. Now, in more general setups, right, we have this abstract notion in relations that says, imagine X and Y are an element of the relation. And also, Y and Z are an element of the relation. This must imply that there is a third item or element in the relation, which is the combination of the first entry, right? X here, and the last entry or the second component of the second relation, which is Z. So basically, X and Z also belong to the relation, okay? So now I'm gonna show you, right, in a very simple proof, that the canonical order on the plane is transitive, okay? So start with 2 vectors, X and Y, and this means that entry by entry, X is greater than equal than Y. So that means entry 1 is greater than equal on the scalar order than the second vector in the same entry. And the same happens with the second entry among X and Y. Understood? Just as a restatement of the definition, right? I do the same with the second part of the statement. So Y is in relation with Z. That means Y entry by entry is greater than equal than Z. That's just a restatement of the definition of the premise of the definition of transitivity. Now, once we have done that, notice that I can just apply the transitivity of the scalar ordering, right? The greater than equal part. And this implies basically that if x1, the entry 1 of the vector x, is greater than equal than y1, and y1 is greater than equal than z1, this must imply, right, that because this is a real line, that x1 is greater than equal than z1. Do you agree?
Yes.
Okay. And then the same happens with the second entry, and we conclude that x2 is greater than equal than z2. This means then that x is in relation with z. Got it? Okay. So in conclusion, remember this notation. X in relation with y, y in relation with z implies x is in relation with z. Okay? This is transitivity.
One question. Is this proof only for this canonical ordering, right? Or for any ordering?
No. So some orders are transitive, other orders are not transitive.
Okay.
Now, what I said is rational orders are both complete and transitive, right? So there are many orders that are not rational in that sense. Okay.
Great.
So we're going to, of course, learn all the details here, right? So there's a lot of qualifications to be made about the notion of rationality, transitivity, and completeness, right? But in the simplest setup, transitivity and completeness are equal to what we're going to call rationality. It's a definition, right? Now, so this is the dictionary part. So this part basically how to study it. First of all, you are not going to be tested in this thing directly. Do you understand? So I'm not going to go in an exam and tell you, oh, tell me by heart what is a symmetry, right? That's not how it works. So basically, you need to learn this because this is a language, right? This is a dictionary that you need to understand in class, right? These are just definitions. So it just names, labels with a property. So you have to learn these properties, nothing else, right? So if you can print it and have it on the side, put it on the iPad, put it on the phone, and then you can check it if you need it, right? Most of the times, most of the things you are just able to refer back quickly, Google it, whatever. We're gonna need most of them not very often, but some of these properties we're gonna need them a lot. So I'm gonna highlight which are them, and let's understand it right now. So the first property basically is a property that is basically very simple and always assumed in most models of preferences. And this is called reflexivity, right? And it just means that X is in relation with X for every X. So if you're modeling preferences, usually we assume reflexivity because it's just such a natural way of modeling preference, right? You say basically that X is in relation with itself, right? In terms of modeling preferences, you say X is, of course, weakly preferred to X, and also because it's a symmetric statement, given that X is also weakly preferred to X, that means you can define something called indifference, right? And we're going to get to that notion in a second, the equivalence relation idea. So you can define in that way the indifference relation. So you can say X is indifferent to itself. Is there any important economical decision theoretical meaning here? No. It's a mathematical normalization, right? So you just decide to model preferences in such a way that the elements X, X always are there. Understood? This is reflexivity, right? So it's just taking the diagonal and keeping it, okay? It's nicer, it's better, it's a convention. So, okay, that's reflexivity. Nothing fancy about it. Now, of course, you can have something that is a counterexample of that, right? So, and we can define x and y being different. So the relation R means that x and y are different elements, right? Hence, in this kind of relation, x is not y. Lucky for us, we're not gonna usually model preferences using this such weird relation, right? X is different, right? So there are, of course, relations that are not reflexive, but all relations that we use for preference modeling are not of this weird type. Understood? Now, completeness is also named in the literature as totality, right? So these are names. I'm writing them both not to confuse you, right? But rather than you actually understand when you read a paper, right? So you're gonna get papers that say preferences are total, or they're gonna say preferences are complete. The modern use is complete, right? The kind of a little bit more classical, more mathematical is total. Whatever, right? Both names are valid. We say that R is complete if either X is in relation with Y or Y is in relation with X, and this holds for every X and Y, okay? So now for terms of preferences, this means, that the preference we're modeling are able to rank any pair, okay? That's a lot to ask, right? It's a big property, but in terms of modeling, it's not really giving you much. But we're gonna get deeper into this. Just know that this is not the main key property of rationality. It's kind of a technical thing we need to assume, okay, to be able to do models. Well, let's not get there, but that's completeness. Now, so transitivity I already defined is here again. So we say R is transitive if X is in relation with Y, Y is in relation with Z. This implies X is in relation with Z. And before going to the asymmetry and others, I also want you to check to this other property called acyclic. And look at this one. It says that X1 is in relation with X2, relation ... xn implies that X1 is Not xn. Okay? So basically this is saying that there is no cycle, right? Because if this would be equal, then xn would be in relation with x1, therefore forming a cycle, right? So you will have x1, x2, relation ... xn, relation x1. You see? So it's kind of a loop. Okay, so that's a cycle. A cyclicity is saying no cycles. Okay, so that's basically it, no cycles. There is this property is going to be important because this is a different property from transitivity. Preferences that are complete and transitive happen to be acyclic. Okay, so if you put together completeness and transitive, right, they are acyclic. Okay, however, being acyclic is not transitive, so it's a different property from transitivity. Why do we need both? Again, it's not to confuse you or to make your life harder. It's just that these two properties are going to be needed when dealing with different kinds of data sets. Okay, so first time we hear data set. So what is a data set? Basically, for us, the primitive in this class, the primitive of a study, the data set we imagine we have is basically a choice data set, which means you have a choice set of alternatives, right? And then you have a choice out of that menu or budget, or choice situation. So you have a choice situation that can be a budget, for instance, a budget constraint. And then out of that budget, you see what people have chosen, okay? Now, from those, we're gonna be able to check sometimes, some properties of the implied relations, right, from the data. And then rationality is gonna be basically mapped to this acyclicity property, okay? Instead, if we imagine we're able to see your brain and know your preferences, then transitivity and completeness will be the way to describe rationality. Short story, this is a complex statement, a complex paragraph sentence I said right now. You don't need to understand it fully, What I'm just telling you is that these two properties, transitivity and acyclicity, will come to our help in different situations, right? And they will be important on how we understand rationality, okay? So now I'm gonna introduce to you the other properties that are also complementary to our study. The first one is called symmetry. We say R is symmetric if you have X is in relation with Y, implies that Y is in relation with X. So that's basically telling you that there are some relations that basically whenever you observe that X is in relation with Y, it has to be also the other way. So can you tell me an example of such a relation in real life? So think, for instance, of two humans, right? And I declare human 1 to be the sister or the brother of human 2. Okay? So of course, let's just say they are siblings, right? So no gender involved, right? So now, do you think X is a sibling of 2, right? Is a symmetric relation? Yes, right. Why? Because obviously if you take human 2, right? So if X is sibling of Y, then Y is a sibling of X, right? So exactly the definition, right? So having tell you this example, can you tell me a counterexample of something that is not symmetric?
Yeah, instead of sibling, saying brother or sister.
So you say, for instance, John is the brother of Anne, right?
Yeah.
So now that doesn't imply, right, that Anne is the brother of John, right?
Yeah.
So yeah, that's an example, right? And you can imagine more mathematical ones, like for instance, the strictly greater than, right? So for instance, 2 is strictly greater than 1, right? This doesn't imply that 1 is strictly greater than 2. So what will be the mathematical example of a symmetric relation? The equal sign, right? So 1 is equal to 2. These are symbols. I can define them. You can say it's not true. It's a symbol, right? Then, of course, in this equality relation, then everything is equal, right? So these are all symbols for us. They don't have any meaning. You give the meaning you want to them, okay? Now, having said that, right, we define symmetry, okay? Why is symmetry important? Usually it's going to be used for defining what is called indifference, as you can imagine, right? So you have two objects which you feel indifferent about, then obviously there's going to have symmetry there, okay? So that's the modeling purpose of it. Asymmetry, as you can imagine, this is the opposite of the other, right? So this is the strict preference, right, part. So you are going to say that if X is in relation with Y, it implies that not Y in relation with X, okay? So this is strictly preferred, right? So a strict relation, okay? And then antisymmetric is a property that is a little bit more mathematical, but something very useful that kind of includes the greater than equal and equal, right? And we say that, for instance, if you have a relation that X are Y, Yx, it implies that X is equal to Y. So this is, of course, mathematical objects have this property, like, for instance, the greater than equal, right? So imagine you have a number X greater than equal than Y, and Y is greater than equal than X, right? So what does it mean, right? It means that X is equal to Y, right? They are the same element in the greater than equal real line object, okay? So that's an example. So for the real line, you have the three cases, right? Symmetry is the equal part. Asymmetry is the greater than strictly greater, right? And antisymmetric is the greater than equal, okay? So three symbols, three properties, okay? Now, of course, this does not exhaust the possibility of relations, right? Relations are super rich language, mathematical language, so there are many relations that we can define. Okay? Now, so that's basically it. I want you to define these other things again, language. So any questions before moving ahead? No.
I have one. Maybe a silly one, and maybe you covered it, but transitivity and acyclic, do those, if you have one, you don't have the other, or can you have both of them at the same time?
So you can have both at the same time,
Okay.
but they don't imply each other. So they are not exclusive. So they can happen at the same time. I'm going to give you more examples later on, but this is an important question. So everyone, that's a typical source of issues and in general answering questions, right? So they look kind of conceptually similarly, and that's great that you see the similarity. There are different properties. So the way you should approach these things is just logically. So what is the main logical difference between the two? And I'm going to give you an example, in fact, in a second. I think I wrote it later, but else I'm going to write it because I changed the version each class. I can write it again. And transitivity, the statement says that if you observe X and Y and Z, then you must have the third link, right? X and Z. So a cyclicity instead, right? It doesn't need basically this complete definition for any triple X, Y, and Z, right? It actually can happen. You're just ruling out certain types of relations. So this can actually work in completeness setups. So yeah, let me write an example. Let me see if I wrote it later, or else I can write it here. No, I didn't, so I can write it myself. Okay, I think I did it in another class. Boom, boom, boom. Yeah. Let me do an example here. So I did this asymmetric relation, which is too simple, so I'm going to erase it and replace it. So acyclicity. Okay. So in particular, right, you can have a relation. Let's take these items, right? A and B. Let's write it like this. Right? And then you also have relation with D. D is in relation with A. Okay, so yeah, so sorry, I'm gonna put here this in relation with D. This is cyclic, it's not transitive. Why? So basically, if I take R, A, R, B, R, E, right? We know that A is different from E, right? Hence cyclic, right? But
Yes.
yeah, you see, since A is here, B is here, transitivity requires that A, R, D, right?
Yes.
However, this is not in the relation. Okay. So the cool thing about what Severin kind of guessed, right, is that these two are obviously linked, but they are not the same. So remember that transitivity is kind of the version of a cyclicity where you complete everything, right? So in other words, and we're going to get to that at the end of this class, you can take cyclic relations and make them transitive, okay? That's what you can do, right? So you can basically take the transitive ones, the acyclic ones, and making them transitive. And basically being acyclic always allows you to make them transitive. So for instance, I can take this here, right? And add the relation that was missing, right? You can see, and then keep completing until I get a transitive relation. So you can take basically acyclic things and make them transitive, but they are not usually the same, okay? They are not the same. I hope you understand this. And again, so that's the cool thing about relations. They are a mathematical object that helps us express properties of preferences, and sometimes in ways that are very subtle, but important for data. Again, this is not just, we like math, but this will become important because in real data sets, usually you don't observe all possible choices from all possible menus, right? So the property that we have to check for rationality is a cyclicity, right? Checking completeness and transitivity is usually computationally impossible. Do you understand? So intuitively, you must know that if you have a huge choice set with a lot of alternatives, right, infinite number of them, then checking completeness means checking every pair, right, which is impossible. Do you understand? Checking transitivity is the same. I have to check every triple, right? But usually in real life samples, right, I just get a realization of choices and menus. So a finite collection of them. So then I can use a cyclicity, right? So it turns out that rationality in real data sets maps to a cyclicity, but of course, if you were to observe in a perfect world every possible choice from menus, then you will map to this completeness and transitivity, okay? And that's a little bit of intuition you will learn in the first part of the chapters, right? So the maps from model to data and how these two properties play, okay? So they are related, but they are not the same. Any other questions there?
Yeah, could I ask a question regarding this example? So in the last sentence of the example, we have that it is required that A is related to D, but it is not in the relation. Is it not in the relation because we are not assuming completeness?
So the relation I define is my creation, right?
Yeah.
I just left it out intentionally. Now that makes the, so let's see if this is complete, right? So you have here basically AV, AVD and E, right?
Yeah.
So there is essentially four items, right? And these four items, right? I basically can run almost all of them. But for instance, A and D is not basically there, right? And A and E is not there, right? So it's obviously incomplete. So there are some pairs that are not in the relation. So yeah, on top is incomplete, right? Now, what you're asking, I get your question is, imagine I somehow complete this relation, right? Will it become transitive? The answer is yes, and that's actually a theorem. So it's not obvious, right? But basically there is a theorem that is called an extension theorem that says if you have a cyclic relations, you can always complete them in such a way that you become transitive, but not only that, but also the strict part of the relation is going to be preserved. Kind of a strict preference are going to be preserved. So that's a theorem that will come in a second, right? But yeah, you're looking at the correct things, but let's not run ahead of ourselves. Just right now, the thing we want to understand is that cyclicity is different from transitivity, right? They are related, but in a very complex way. Right now, they are different. Mathematically, logically, different properties, okay? And yeah, the reason why they are different, you can try to intuitively say it's lack of completeness, right? But it's a little bit more complex than that. It's just two different definitions, okay? Good.
Thank you.
I have one question. I wonder what's the difference between the completeness and symmetry?
Sure. So symmetry is just a statement about, So completeness, basically, the quantifier says that take any pair in the choices X and Y, and it has to be that either X is in relation with Y or Y is in relation with X. So the quantifier is the difference. This is a universal quantifier, right? So for any X and Y, X is in relation with Y or Y is in relation with X. Now the symmetry, right? What this is saying basically is take as a premise one relation. So already exists, one relation is there, right? Then the fact that this relation exists implies that Y is in relation with X. So it also implies that the mirror image version is there, okay? So examples of this, take the real line and the equal sign, right? Equality between two numbers or two numbers basically is a symmetric relation, right? But it's not complete because you have numbers such as 1 and 2 that are not equal, right? So they are not in the relation. You understand? So, however, 2 and 4 to be divided by 2, so the rational number 4 over 2, right? These are equal, right? And of course, that implies that 4 over 2 is equal to 2. and also implies that 2 is equal to 4, 2. So let's do that. So let me do it here. Example. So this is a good example, actually. So symmetry and not complete. So imagine x is equal to the real line, right? And I define basically the relation A is in relation with B, if and only if, right? A is equal to B. Take, for instance, 4/2 is equal to 2, right? This implies that 2 is equal to 4/2. However, it is not complete because two basically is not equal, right? For instance, 2 and 1 are not in the relation. Right? Do you understand? So this is interesting, right? Because this is so simple. So, something you have used all your life, equality, but we're just applying logic to it, right? So I define a symbol R that says equality, okay? Equality of numbers. So you will agree that the number 4/2 is equal to 2. The first thing I want you to realize is that, in high school, they teach us to simplify, right? Simplification is actually using relations, right? They are using the equivalence relation. They're saying this number, which is a rational number, 4/2, is a different number from 2 in principle, right? However, we put them in the equality equivalence class. So it's an equivalent number, right? But it's a different number. Do you agree with that? So the different elements, right? One is rational, the other is an integer, right? They are even in different sets, right? So inside the reals, right? So now 4/2, rational number is equal to 2 under the equality of numbers, right? So equivalence class. So this is the relation. Now I'm gonna check that this relation is symmetric, right? So if A is equal to B, right? B is equal to A. That's obvious, right? So I just put an example, right? Okay, but at the same time, this is not complete because, for instance, take 2 and 1, they are not equal, right? So hence there is a counterexample where I have two numbers that belong to X, to the reals, that are not in the relation, right?
Where does 1 come from? Because I only see 4/2, and it looks like it's two totally different relations.
So no, R here, so each example is a different relation, right? So my point is that basically the symbol R is a general name for many different ideas we're using, right? So in particular, in this example, I define R to be equality on the real line, okay? But as you saw in the previous examples, it can be really anything, right? So the R is an all-purpose symbol for different ideas we use for different choices. So this is a modeling technique. It's like the utility function, right? So basically, I change the utility per exercise, right? So sometimes it's utility of Douglas, sometimes it's CES. This is similar. So it's just the relation counterpart of the utility, okay? So there is, this is a particular relation, and this happens to be the equality of numbers. So a little bit the way to understand this, and I find that useful, is basically you try to see it as pure symbols, right, and logic, and try to understand within the context. So in particular here, this relation is equal to the equality sign on the real, okay? So now the first thing to check, your question was, is there something that is symmetric yet not complete, right? And this is such an example. First of all, it's obviously symmetric, right? Because in the equality sign, if element A is equal to B, then it has to be that B is equal to A, right? That's just the property of this symbol. Now, so symmetric. Now, however, is it complete? How do you show that something is not complete? By showing a counterexample, right? So take two numbers here, 2 and 1, and I show them that they are not in relation, in equality relation with each other, right? Because 2 is not equal to 1, right? Hence, that order pair, 2 and 1 is not in R. And also, 1 and 2 is not in R. So formally, right? Not in R either, right? So basically, neither A and B or B and A, in this case being equal to 1 and 2, are in the relation. So hence, this equality only works for certain numbers. It's not defined everywhere. Do you see? So
Yeah,
now,
I get it.
yeah. So that's a good example. And again, like why maybe this is confusing, because in the real lines, usually the order we use is greater than equal, right? And that one is complete, for instance, because it also includes the equality, right? And includes the greater part. So greater than equal is complete and transitive. But the parts of that, equality and strict inequality, they are not complete, okay? Okay, so great. So now we can use these properties to define useful relations. The ones that we need is basically called equivalence relation. So we say that an equivalence relation is another kind of order, and we're gonna call it by I because of indifference. And basically an equivalence relation is gonna be a type of relation that is, at the same time, has three properties: reflexive, symmetric, and transitive, okay? So the key example that we just wrote is the equality on the real line. So that's basically a type of equivalence relation, okay? So let's go back to this example I wrote. So is it reflexive? Yes, because any number is equal to itself, right? So check. It is symmetric, we just showed is symmetric. Is it transitive? Yes. If two numbers A and B are equal, and you have number 2 is equal to a third number, then you have that the first number is equal to the third number, right? So equality is, of course, an equivalence relation. Right now, what I want you to remember is that we call an equivalence relation to any relation that has the three properties: reflexive, symmetric, and transitive. The way we use it is usually to model indifference, right? So we say two things are indifferent to each other, right? Then they happen to be usually reflexive, because anything is indifferent to itself. Is symmetric, right? Because if you're indifferent between X and Y, then Y is also indifferent to X. And finally, they're transitive, right? So the indifference is going to take transitivity easily, because have X indifferent to Y, Y indifferent to Z, X indifferent to Z, okay? So equivalence relation basically is a way to model indifference, okay? And three properties define it. Any question here? So it's just a definition, okay? Indifference. Now, there are some names we're gonna repeat it again and again, but I'm gonna call them also, this is a proper name, but also has properties that define them. I'm gonna be very clear what we mean, but just try to remember them. It's a little bit easier. Pre-order, right? So this is, again, is a dictionary class. So there is just names here, and we're trying to make sense of them, but it's not needed that you know them by heart, right? It's just the properties is the important part. So a pre-order is basically a relation that happens to be reflexive and transitive, okay? So this includes all the diagonal, right? Plus it's transitive, but it doesn't need to be complete, okay? So that's, of course, the main issue with the pre-order. Now, when we call them the partial order, now you are gonna add one more property: is reflexive, transitive, and antisymmetric, right? And in particular, right, for instance, the partial order usually rules out the existence of an equivalence relation, right? Because you have to be antisymmetric. And finally, this object is super important. It's called the linear order, which is a complete partial order. So basically you have everything you can rank, and then basically you have here on top of the partial order properties, you add completeness to it. Now, why do we care about the linear order? So the linear order is super important because this is the way we model strict preferences. Okay? So strict preference relations basically are called linear orders. So linear orders, you can also call them. These are lists in Excel, right? Where you ranked the best items in terms of something you want to buy. So say tomorrow you want to buy a new vacuum cleaner, right? So you go on Amazon, check all the reviews, you know, the Wirecutter that does reviews for vacuums, and you check, you know, whatever sources you like. You ask people. You do a spreadsheeting, right? So you start ranking all the vacuum cleaners according to which one you think is the best, right? So this simple exercise of ranking strictly, this vacuum Dyson is better than this second vacuum and this third vacuum and so on. If the ranking is strict, is a linear order. So why basically, you know, reflexivity again is implied because you always say something is in relation with each other. That's just a normalization. So any item is in relation with itself. But then basically you have that is transitive, right? So position in the list, and is antisymmetric, which makes it basically a strict preference relation. Okay. So that's so let's go back to the antisymmetric part so you remember. So antisymmetric means that if you have this chain of x is in relation with y and y is in relation with x, it must mean that x is equal to y, right? So if you break it apart, right, it means that you cannot have that x is in relation with y and y is in relation with x at the same time if x and y are different, right? So think of a list, right? You cannot have that Dyson is above another vacuum cleaner, and in the same list, the second vacuum cleaner is above Dyson. That's what this is saying, right? So this is a kind of elegant way that allows you for having reflexivity, but it's just describing a strict preference relation. Okay? Do you understand? Okay. So in other words, the linear order is a fancy way to say you were able to rank all your preferences in an Excel spreadsheet, right? In a strict way. Okay? That's what it means. And then, of course, the complete pre-order is whenever you couldn't decide between two brands of vacuum cleaners and you say, okay, these two, I'm indifferent among them, right? So, you know, in the top, there is a tie. Whenever in your list there is a tie, right? Then you are in the world of pre-orders, right? And if the list is complete, you know, it's a complete pre-order. So that's basically the still, you know, a complete and transitive relation, but now you allow here for indifferences, right? So we're gonna learn them again, but that's a little bit the main reason we need this. And I'm gonna skip this part so you can read it yourselves. These are names in order theory we use for different sets that are ordered, but for me, it has become less important. The only one that really still matters to me is the equivalent class. So here I'm gonna ask you something. So who among you are undergrads in econ? So a lot of you, right? You told me yesterday. So what is an indifference curve? Can you describe it? Think of a plane. So you have two goods, right? Saying, you know, two assets, you know, Moderna and Pfizer, right? So that's your portfolio of assets. Now tell me, you know, what is first the choice set, right? So in this situation, so these are quantities of stocks you're buying, right? So you can imagine they are expressed in dollars. So basically you can buy fractionally and whatever. No, let's say you can buy fractionally. So it's just the whole plane. So it's R2, that's the choice set. Again, you are only allowed to buy, so you are only allowed to own them. Not, so basically it's a positive plane, R2 plus. Okay, that's the choice set. So define what is an indifference curve there. So can you describe it to me?
Yeah, I think that are all the possible combination of the two choices that give me the same utility, the same level of utility.
Okay, so basically I have some preferences over vectors in R2, right? I'm gonna define that as preference over assets, right? So an asset is a vector, right? Having quantities of fractions of each of these two stocks, right? So, and then, a relation is gonna be ranking them all. Now, an indifference curve formally is very close to what Juan Sebastian said. It's basically is all the items in the choices. So all the portfolios, right? All vectors in R2 such that y is indifferent to x, right? So all of them, x is in relation with y and y is in relation with x at the same time. Hence, both are equivalent in terms of the relation, okay? So here, notice that I don't make a reference to the utility because we don't have utilities yet, but is the ordinal equivalent, right? So basically I'm saying these is the space is a set of alternatives such that they have the property that y is indifferent to x, okay? Now, of course, from undergrad, you know that a special example of this equivalence class is the indifference curve, right? So the relation is going to be fully defined by a utility function. And then I can say that any asset that gives me the same utility, right, is going to be in the indifference class, in the equivalence class, in the indifference curve. And why is indifference curve? Because it's just R2, right? So it's 2D. So therefore it becomes a line, right? Now imagine you have three items. Now it's no longer a curve, right? It's kind of a weird object in 3D, right? And then you go into 4 dimensions, and in general is a set. And we call it in general the equivalent class. So the equivalent class is basically an indifference surface, an indifference set, okay? This is an important object, and it's just the set of all alternatives that are indifferent to each other, okay? Give you the same ranking, okay? So in the example of the list of vacuum cleaners, there's going to be some items that are ranked the same, right? So those are essentially the equivalence class, okay? The ties. Understood? Now, if it's understood, can you tell me, let's go back to this example. With this relation, with the equality relation on the reals, can you describe the equivalence relation, the indifference curve or the equivalent class for an item such as 2? So basically this is equal, right, to all items in the reals, right, such that y is equal to 2, right? That's a way to describe this. So you take a representative of the equivalent class and you can say, you put these brackets and you say, these are all the items that are equivalent to this representative, right? So examples of items that live here. You have here, as we defined before, 4, 2 belongs in the equivalence class of 2. Right? Do you see?
When you have elements in your equivalence classes, are different calculations considered to be different elements? For example, 4/2 is a different element than the root of square 4 is a different element than 2 itself, but all of them are equivalent to 2. So is taking any calculation of numbers in the reals, each one considered an individual element?
Yeah.
Okay, yeah.
That's a good question, Severin. So what Severin is asking is that, are there functions that respect the equivalence relation, right? And if not, is there a name for them, right? So basically we have a name for them. So there are functions, in fact, that may map different elements, such as 4/2 and 2, to different numbers. Those are called ill-defined because they don't respect the equivalence relation, right? Okay, so I'm going to give you an example. Again, this is important. Here is such an example, right? Imagine a function f of p over q that is equal to p minus q, okay? So take two numbers, 2/4 and 1/2. They are on the equivalence relation, but they are mapped to different things, right? Because the first one is 2 minus 4, which is equal to -2, and the second one is 1 minus 2, which is equal to -1, right? So this is a crazy function that we call ill-defined. So it's bad, right? We don't use them because it's taking two numbers that are the equivalent to each other, right? So two fractions, 2/4 and 1/2. They are different elements, right? Yeah. But this crazy function I defined, right, maps them to different numbers, right? This is called ill-defined. So basically, in contrast, well-defined means that if x is equivalent to y, or in general, there is an equivalence class that puts x and y in the same set, then, f of x is equal to f and y. This is, important because you can imagine that when you're dealing with utilities over, for instance, any kind of choices, for instance, assets, right, portfolios, you will want that you get the same utility for all elements in the difference tree, right? So basically, these are the limits of modeling. Now, all of this, is interesting because a lot of what you learn in undergrad and a lot of what you learn already, so is already, pretty true. So it's very, it's already usable, right? But math is so general, right? At this level, you can define these crazy objects, right? And that's why orders are important, because they allow you to be very formal about what things are the same in a set. And in the end, right, the trick that we're going to use again and again is basically try to take all the elements that are indifferent to each other, map them to a single object, right, project them to the equivalence class, and then basically move to a choice space where all indifferent objects are mapped to a single object. And then you can just play with it. Why this is important? Because we don't do it because it's complex. We do it because we need to do it. The reason is that theorists thought that indifference is an important part of human behavior. I think that's something that we can argue about. I'm not convinced indifference is actually natural, but whatever. This is something we can discuss about. But theorists are convinced that indifference is in fact important. Indifference becomes very relevant in terms of modeling preferences when dealing with infinite choices, okay? Because as you can imagine, right, so if you have a continuum of alternatives, right, you don't want to be thinking about, how to map things that give you the same return, for instance, right? So do you want to really run them differently, right? Or do you want to just write all the things that have the same return will be the same? So that's kind of one example where you want to map things to a smaller dimension. So in general, indifference is something we use, is an important part of modeling preferences. And hence we need to use equivalent classes, because the whole trick is going to be to use equivalent classes to change our choices to a simpler one, where there is everything that is the same is projected to a single item, and then use a strict preference over there, right? So in other words, the true theory of utility maximization is going to be done in a strict preference land. So, and then, we can extend it easily to the indifference case by playing with these equivalent classes. So, that's just a footnote of the technical things that are going to come. But right now, you don't need to understand fully. So don't get scared. Good. So what do we do with preferences? Remember, preferences are the kind of black belt level of utilities, right? So you maximize utilities, right? That's what you do in undergrad. You take a utility, you maximize it, right? So here we do the same. So we take a choice set and we maximize it with respect to the ranking, right? And so, here there is some technicalities. The first thing is we're going to define a maximum element. such that there is no other item that is strictly dominating this thing here. Here, I define something that we're going to repeat again, which is you take a relation and you can always break it into two parts. The asymmetric part of a relation, we're going to usually call it P, or kind of the strict part, and is defined as the following. If X is in relation with Y, but it's not the case that Y is in relation with X. So we usually use this part of the relation to represent the strict preference relation, right? So sometimes you say, this portfolio is much better, is strictly better than this other, okay? So this is about the strictness, okay? And of course, you have the opposite, which is the indifference relation, which we just discussed, which is the equivalent class, right? So X is in relation with Y, Y is in relation with X. So you take two portfolios that give you the same return. That's one example, okay? So now the names are a little bit telling. The capital P means strictly preferred, and the other means, indifferent. And here we're just saying a max of a set, given the preference relation R, is all the elements in X such that there is no Y that is strictly preferred to X. So there is nothing better, right? So this is a nice definition because it also allows you to maximize preference relations that are not complete, right? So it's much more powerful than just maximizing utility. So it's a powerful notion. But in general, it's nothing crazy, right? So remember to the idea of the vacuum cleaners and the Excel spreadsheet. So how do you pick in the end your vacuum cleaner? So you go to the list, right? And you pick the one that is not dominated by any other, right? So you pick the one at the top of the list. That's what you're doing, right? So that's basically preference maximization, okay? And then you can have other alternatives such as upper bound, which basically means that these are all the X's that are dominating the rest. And of course, these two are different, and in some cases they are equal. An example where they are different is, imagine you have A, B, C, and the relation only says A is the strict preferred to B. There is nothing more. So in that case, right, what will be the upper bound? So it's the empty set, right? Because there is no thing or alternative that dominates all of the others. Do you agree? For instance, A only dominates B, but it doesn't dominate C. Do you understand? So by definition here, this thing is empty. Okay? So if we were maximizing these preferences, right? There is, according to the usual notion of utility maximization, such that the utility of the item you pick is above all others, right? This thing will be empty. So there is no maximizing object in the usual sense. But there is this new definition, the maximum element, that is more powerful, that says, look, just take the items that are not strictly dominated. So A, is there anything that strictly dominates it? No, right? C, is there anything that strictly dominates C? No. Is there? B, is there anything that strictly dominates B? Yes, A, so it's out, right? So the maximum is A and C, okay? Agree? Okay, so a lot of, historically, why people move to the world of preferences is because they are very powerful, right? You can do things that you cannot do with utilities. When you are in utility land, you can only use completeness and transitive, right? So when things are complete and transitive, that's basically mapping to utilities. Things are very nice, right? Because essentially these two objects are going to be equivalent. Okay, let's do that. So I'm going to do another example. I'm going to show you that the two objects are the same. So let's do this as a problem in class. And I'm going to ask you to show it. So basically, let's say I have A, B, C, and I have a complete and transitive relation. Sorry. So basically what I'm saying here, the way I'm defining it is I don't want to write the full relation, right? I'm just saying this is complete and transitive, and the strict part is such that A is better than B, better than C, okay? So I want you to compute the M of X, and I want you to show that this is the same as max of X for this particular case. So who wants to do it? Very easy.
So it should be A.
Yep. So this is just equal to A, right? There is nothing fancy about it. And of course, I'm gonna leave you to think about as a proof for the next class, right? So how do I formally prove these two things are the same? So look at the definition in the first part, right? So which is the only object that is not strictly dominated by anyone? A, right? Let's go to the second one. Which is the only object that is above the other one, right? For all of them, right? Is A again, right? So that's it. So A is the only object. Okay, so you can basically show that if the two objects are complete and transitive, so the upper bound and the other are the same. Now, so this is a level of mathematical, order theory that is too high for the actual class. The only thing you need is really to know the concepts and so on. We're going to use them again and again, but we're going to focus the class. This is a first year class. We're going to focus on transitive and complete orders, okay? This is our main focus. We're going to sometimes deviate to extensions of this model, meaning we're going to remove completeness, right? And, it can be that we can remove transitivity as well, but then things are going to be hairier. The main point is you actually need to understand this, because the point is that in the full theory of decision theory, the high level, we don't need to assume transitivity and completeness, right? The rational model, which is the main model we study, assumes transitivity and completeness, and this becomes utility maximization. So a lot of it is going to be building up this connection and coming back to utility, okay? But remember, right, that the mathematics that people have developed in decision theory can go easily beyond the transitivity and completeness, right? But we're not gonna go very frequently out of the transitivity and completeness, right? So again, so short story for today's class, this is kind of very high level, very math, a lot of dictionary. So if you really go back to the class and think what I'm doing is basically stating definitions, right? And then playing with definitions, giving you examples and counterexamples. So this is a classical kind of math class, introductory math class. We didn't prove anything really. So this is not the typical class, okay? My main point is this class is in the refresher for a reason, right? It's designed to give you kind of a dictionary, right? So these are things you need to know in order to process better. But it's super simple. If you read it, get through the definitions, and try to understand what are them, it's just like, learning a name. So if you want to learn, for instance, the language, so I was trying to learn French, right? So what do? You receive a list with verbs, trying to conjugate them, different times and so on. So you have to learn it, right, by heart. You say, okay, I'm gonna learn, this verb and so on, the typical to be verb for any language is classic exercise. That's a little bit what we're doing here, okay? So that doesn't mean you know French, right? Or that doesn't mean you cannot use a cheat sheet to be able to talk with people, right? So that's what we did today, okay? So now, having said that, any other questions?
Sorry, Professor, so this file is on Slack?
So it's on GitHub. So let me show you. So yesterday in the general channel before the class, I said, enter to the GitHub channel and you can download it. So let me stop the recording and then we can go through the logistics, okay?